Hello guys, welcome on Tesla Adventures. In this video, we'll discuss the combination of slabs and we'll compare them with the combination of resistances. And we will also find out the formulae for the equivalent thermal conductivities. So starting from the parallel combination, you can see that these two blocks are connected in parallel, and the parallel connection can be seen by the fact that the total heat is passing through them, and the total heat is passing through them simultaneously. In series combination, the heat passes from one of the slab and then it passes from the other one. So this is the parallel combination, and that one was the series combination. So you can see that there are two blocks of area, cross section area A1 and A2, and their thermal conductivities are K1 and K2. A total heat current of Q by T is passing through them, and these are maintained at temperature T1 and T2. Obviously T1 would be greater than T2. The length of these two slabs is L, and therefore we can say that by the analogy of current electricity, the equivalent resistance of these two slabs will be 1 upon R equivalent, will be 1 upon R1 plus 1 upon R2. Now you can see that R equivalent is the equivalent slab of these two. So we can say that equivalent slab is analogous to combination of these two slabs, and R equivalent will be equal to L, which is the combined length, which is also L. So it is L by K equivalent into total area. Now the total area should be that area from which the heat is crossing. So the total area from which heat is crossing is A1 plus A2. So here it would be A1 plus A2. And R1 will be equal to L1 by K1A1, and R2 will be equal to L by K2A2. So you can see that this is K equivalent into A1 plus A2 upon L will be equal to K1A1 by L plus K2A2 by L. So K equivalent will be equal to K1A1 plus K2A2 by A1 plus A2. Now if area is equal, if A1 is equal to A2, then K equivalent will be equal to K1 plus K2 by 2. So this is the parallel combination of slabs, and you can see that in parallel combination the heat current through both the slabs might be different. It is possible that the resistance of this upper slab is different and the resistance of the lower slab is different, but the temperature difference for both of them is T1 minus T2. Therefore the heat current passing through both of them can be different, but the temperature difference would be same, similar to the fact that in parallel combination potential difference across these two resistances is same, but current passing through them might be different. Now in series combination, these slabs are connected one after another. The length of slabs is L1 and L2, and the area is same, which is A. Let's suppose area is A. Now we can say that this combination is equivalent to a series combination of two resistances R1 and R2, and therefore we can write down the formula that R equivalent is R1 plus R2. So R equivalent will be the equivalent slab resistance, and the equivalent slab of these two would be a slab of length L1 plus L2. So its equation would be L1 plus L2 divided by K equivalent into area, which is A, because the combined area is A and the area of the equivalent slab would also be A. Now R1 is equal to L1 by K1A and R2 is equal to L2 by K2A. So you can see that R equivalent, if we substitute these values in this equation, then L1 plus L2 by K equivalent into area will be equal to L1 by K1A plus L2 by K2A. Cancelling this A with A, so K equivalent is equal to L1 plus L2 upon L1 by K1 plus L2 by K2. Now if L1 is equal to L2, K equivalent will be equal to 2 K1 K2 divided by K1 plus K2. Okay, so this is the formula for equivalent thermal conductivity in series combination. Now let us move on some questions which would explain these concepts with more concrete way. So let us move on the numericals. In this question, you can see that there is a semicircular rod which is joined end to end with a straight rod of same area of cross section and same material. So let us suppose that there is a semicircular rod, this one, and it is joined in series with another rod of same area, in fact in parallel, like that, because it is given that this straight rod is forming its diameter. Okay, these junctions are maintained at constant temperature, and it may be possible that this is at higher and this is at lower temperature, and let's suppose the radius is r. So we have to find out the ratio of heat transferred through the cross section of the upper rod to the heat transferred through the lower rod. So let's suppose that the heat which is transferred from the upper rod, heat current, is I1, and the heat current transferred through the lower rod is I2. And the resistance of the upper rod is R1 and the resistance of the lower rod is R2. And let's suppose that the radius of these rods is smaller. Now we know that the resistance R1 will be L1 by KA. Now K and A is same. So L1 of this length of this semicircle would be equal to pi r, and this is K, and R2 will be equal to L2 by KA. Now L2, which is the length of this straight rod, will be equal to 2r divided by K into A. Now we can see that we already know that this is a combination in which the resistances are connected in parallel, and for parallel combination, let's suppose the current passing through the upper one is I1 and through the lower one is I2. So we know that in parallel combination I1 by I2 will be equal to R2 by R1. Okay, so I1 by I2 will be equal to R2 by R1 is 2R by pi r. So cancelling R with R, the ratio of the heat currents would be 2:pi. So the correct answer will be 2:pi. This is 2. Now let's move on the next question. In this question, you can see that there are 3 slabs which are combined like that, and their thermal conductivities are different and their thicknesses are same, T1, T1 and T1. In fact, T1, T2 and T3, their thickness is different. The area of cross section of each of them is same. Now in a steady state, this combination behaves like a single slab, and we have to find out the effective thermal conductivity of that single slab. So let us first of all see that these are in series combination, and the resistance R1 of one of them, first one, is equal to L by Ka. Now you should always know that the length which is used in resistance, L by Ka, is the length along which the heat travels. So heat is traveling like that. Okay, so the length of this slab would be T1. So it is T1 by K1A, R2 will be T2 by K2A, and R3 will be T3 by K3A. Now in series combination, R equivalent will be equal to R1 plus R2 plus R3, and therefore the equivalent resistance would be equal to T1 plus T2 plus T3 divided by K equivalent into L. This is very important to note that when we will draw the equivalent slab of these three, then the length of that slab should be at T1 plus T2 plus T3, which is the combined length of this combination. And the area is common, so area is A. So R1 is T1 by K1A, R2 is T2 by K2A, and R3 is T3 by K3A. So cancelling A with A, you can see that K equivalent will be equal to T1 plus T2 plus T3 upon T1 by K1 plus T2 by K2 plus T3 by K3. And from now onwards, you can memorize this result for n slabs. So for n slabs, there would be the n terms on the upper side and there would be n terms on the denominator. Now we move on the next question. In this question, you can see that there are two walls and there are 6 slabs which are combined in parallel between these two walls. These two walls are maintained at constant temperature, but the temperature of each wall is different from one another. Now we have to find out the equivalent thermal conductivity of the system, and it is mentioned that this distance is equal to D. Now you can see that if the resistance of this slab is R1, then this is also R1 and this is also R1. And if resistance of this one is R2, then this is also R2 and this is also R2. So you can see that there are 3 resistances which are in 3 equal resistances R1, R1 and R1 which are in parallel, and along with 3 another equal resistances R2, R2 and R2 which are also in parallel. So the equivalent resistance of this system would be the combination of this one. I can write that 1 upon R equivalent will be equal to, you can see that R1, R1 and R1 are in parallel, so their equivalent would be R1 by 3. So you can use a single resistance of R1 by 3 and R2 by 3. In fact, this is R2 by 3. So this would be 3 upon R1 plus 3 upon R2. Now the equivalent resistance, R equivalent, will be equal to L by Ka, and L is D and K is K equivalent, and the total area, let's suppose the area of single slab is A, then the total area would be 6A. So R equivalent will be equal to 6A into K equivalent divided by D, and this is 3 by R1, where R1 is equal to D by A K1. So this is D by A K1 and R2 is equal to D by A K2. So cancelling out this D and this A with A, you can see that K equivalent will be K1 plus K2 by 2. So the correct answer will be option number B. Now we move on the next question. In this problem, you can see that there are 2 identical square rods of metal which are welded first of all in series like that, and their ends are maintained at the temperature 0 degree Celsius and 100 degree Celsius. So let us write down that the resistance of this square rod is R1 and the resistance of the other one is R2. But it is mentioned in the question that these are identical square rods, so resistance would be same. So in this case, the equivalent resistance would be equal to 2R, and in this case, the equivalent resistance will be equal to R by 2. So in the first case, it is given that the 10 calorie heat flows through this combination in 2 minutes. So the heat current in the first case will be 10 by 2, and that would be equal to delta T, which is 100, divided by R equivalent, which is 2R. Okay, so you can see that R will be equal to 10. Now we have to find out the time which would take, the time which 10 calorie heat would take to flow from this combination, which is the parallel combination. So now again, let's suppose that the time taken by this 10 calorie heat is T. So in parallel combination, the temperature difference is given as same, which is 100, and the equivalent resistance of the parallel combination will be R by 2. Okay, so the value of R is 10, we have already calculated. So 10 by T will be 200 by 10, and that is 20. So the T will be half. So it is equal to 0.5 minutes. Okay, so the correct answer would be option number B.